Okay. I want to talk about single slit diffraction today. That's section 33.4 in your text. Now, we've done double slit diffraction. We've done multiple slit diffraction. That's a diffraction grading. And now we want to work on what happens just goes through an opening, a narrow single slit type opening. And the effect is kind of similar to what you would expect. There's a diffraction effect if the gap is small enough compared to the wavelength of light. And we'll address that more in the next lecture. Let me just give you an idea of what it looks like. So if you look at for a slit like this, and you have light going through it, let me draw this in black. And you've got light coming through it, a plane wave of light. This is just light coming into a light wave going in. It will diffract such that out here in what we call far field, a good ways away, we'll say a meter or so away, you'll get a pattern that would look a dark one in the center, excuse me, a bright one in the center, some dark lines, small dark lines, a bright line. It starts to fade out though a little bit. A little bit bigger dark line. A little smaller line, and then of course you can see how this is going. It's going to get dark. A lot like that. So that's kind of what you would see from a light perspective. I got red light coming in, that's what I would see. The dark, of course, is where there's destructive interference, where there's no light there, so in a completely dark room you wouldn't see anything. And of course the red is where you see the red light from the laser or whatever coming into it. Laser would work a lot easier, a lot more light intensity there. Now, single slit diffraction. Now, how do you analyze this? I mean, we could go through the whole analysis. That's more of an optics type course or a pure optics course. I will say I want to introduce the concept of the Huygens principle. And basically, what Huygens said was that on this wavefront here, that each point on the wavefront is like a little spherical, they use the term wavelet, or like a little bitty wave, like a point of source of waves, like a little bitty, is a point source of charge. Think of this as little bitty flashlights that just going out one direction, out, just spread out like this. So what you can think about it, as this goes through here, as a light that comes, as it's in here, think about each point. Each point along this, you can think of this, and I can go blah, 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 all the way down. You can think of this as these spherical waves, and in the far field out here, as we go further, a good distance away, a meter or so, if you do this analysis, and look how these waves interfere, basically, he says, and Huygens says, that the shape later, as the wave propagates, and propagates means what, Locke? No, that's not it. Dayton, what's propagate mean? Dayton. Okay, you don't know what it means either? Okay. Let's see. Who else? Cameron? You don't know it or not. Anyone? propagates. Oh, so you want to try the Angel. As it continues, right? As it continues. Very good, Angel. Good job. You got that. So as the wave continues on for a little bit, what we'll say is that the wave front is a tangent line. Remember, tangent line would be like, that would be the tangent line on that little wave front. So where these two all interact, the tangent line of those interactions to all the wavelets. Okay? Now that's Huygens principle. And the book goes through, they show you how you can use Huygens principle to solve single slit diffraction. I think that's more for an optics course, or especially more in class where we have stuff to do that with. We don't have that right yet. What I will say is, I will look at the results from that. And if you look at the results from that, what you'll see is that the angle, what I'm going to say, the dark fringe here, this angle theta, of course this would be, they use theta p for the dark fringes. This would be a different one. This would be, here would be p equals 1, p equals 2, and of course p equals 3. These are not the dark elves, these are dark fringes. But we say that, you can say that theta p is equal to the p, which is the number, it's just numerical from it, lambda over A. Now where do you think lambda over A comes from? Well, you can go through that. Lambda is from the wavelength of light, and they're saying that A is the width of that fringe. Excuse me, the width of the slit. How wide that slit is there. Okay? That's how wide that slit is. Now, how long up and down it is would be how the thickness of that slit. Okay. Now, that would be the angle for it. If you want to look at the y position, that's where yp would come from, y position of it. That would give you p lambda L over A. Again, we're going to say this distance is L. Lambda is the wavelength of light here. Wavelength of that light. Now give us position, and of course the width of this slit, if that's where the dark is and that's where the dark is, the width of that center slit there, the width of the center slit would just be 2 times y sub p, and that's where that book gets 2. And they say p is 1 for that center slit, so that's the first dark fringe, p 2 lambda L over A. That makes sense. Now, let's think about this. Notice what we see in this equation. This is why we went to it. If A gets smaller, this gets really, really small, the width of that fringe gets really, really big. So W, the width of the center fringe, they call these things fringes. The width of that center fringe gets bigger. So you see a greater diffraction effect as that gap gets smaller and smaller, and you basically get closer to the wavelength of light itself. That's important. As A gets smaller, width of the center. So when does diffraction kind of become an issue, and when can we ignore an issue with diffraction? That's actually a really good question. Now this is single slit diffraction. One thing I did want, you do get a similar, I want to graph this on the screen, and if you look at this, do this in red. If you look at this as intensity, you'll get pretty much about nothing here. Go up a little bit, up a little more. You'll get, kind of dies off like that. This actually is a function you see a lot, something that you'll see a lot with this. Of course, they call this the central maxima. I call it the center fringe of it. Of course, they talk about the, this would be P1 and P2 there. If you do optics, you're going to see functions like that a lot. I don't want to give away too much of the story going forward on that, but you'll see this function. You can mathematically model this using mathematical functions, and those have some interesting math behind it. Let's just say that. But going forward, this is the key. As that gap gets smaller on that center slit, on that for this case single slit diffraction, single slit, width gets bigger. So when can we start seeing these effects and when can we not? That's going to be next lecture. Now I'd like to show you this. Unfortunately, the way we're doing it, I don't think we're going to see it real well. It'll basically just show the light spread out. I can try this here. I'll try this one more time. And we'll get the green laser up from the other day. As you see. Get the light. We'll take our thing we have here that's going to produce. Now, if I hold it right there on that slit, oh, that's a grating. No wonder the big one's a grating. Because it's shining here. You see all that? Well, is that a grating? If I shine it right here, it's hard to see the ones past the first order on that. You can see them on the edges. Yeah, this is a single slit here. You can see it start spreading out with this one. Fortunately, we need a lab on this. The lab's going to go up today, but there's going to be some simulation work. But single slit diffraction, I will tell you, you can see single slit diffraction yourself. So try this at home. So everyone do this. Everybody ready? You ready? Take your fingers like this. We're going to put them really, really close together. And I want you to look at a light source, like up here. If you look, get them almost touching, you'll start seeing, it's like they touch and almost, you'll start seeing little vertical lines. Those vertical lines, now it's not exactly what you see here, but basically you're seeing diffraction on your own. And honestly, stuff. Need a bright source, you can see a little diffraction there. Okay? Alright, so that's single slit diffraction. Math is real similar to what we've seen before. Let me work an example. There's some in your book and stuff on that. But let's talk about this next lecture.